tonight is National Science on Screen Evening across the country. So the Martha's Vineyard Film Center, along with 28 other independent cinemas, are screening science-related films. And as you know, Science on Screen is funded through the Alfred P. Sloan Foundation and administered through the Coolidge Corner Theater Foundation. So from all the way here on our tiny island on the vineyard all the way out to California, there's a national evening of films related to science and so on and so forth. Tonight's speaker, Max Holmes, has a Ph.D. in chemistry and hydrology and is the senior scientist and deputy director of the Woods Hole Research Center right across the sound there in Woods Hole. He came over and joined us tonight. And his focus, as I said, is on permafrost and rivers and watersheds and how their thawing will affect the climate as that happens. He has ongoing projects in many of the Arctic circles. He's actually almost been to Dawson City, I think he mentioned. He's been up into the Yukon there. And in 2015 was named a National Fellow of the Explorers Club. So I think without further ado, we'll have Max come up here, give you a presentation before this wonderful film.
Thanks for that introduction, Gary, and thanks to all of you for coming and to the Film Center for the invitation to say a few words tonight before the film. Let's see, I'm going to dive into my PowerPoint if I can get this to show up. And if not, I'll just... There we go. There we go, okay. Let's see. Before I start to talk about permafrost, which is what I really want to do, I'm going to talk a little bit about science in Woods Hole. And if you're like most people around the world, maybe you're not, but most people tend to think of Woods Hole as all one place. I thought that before I came to Woods Hole in 1995, 22 years ago or whatever that is. I thought it was all one research institution, but in fact there are several different places. So my brief sort of 1-minute history of Woods Hole. In 1888, the Marine Biological Laboratory was founded. They're still there. In fact, before 1888, there was already some science going on in Woods Hole, sort of a precursor of the National Marine Fisheries. 1930, the Woods Hole Oceanographic Institution was founded. They're the biggest guys in town. 1975, at the Marine Biological Laboratory, the Ecosystem Center was founded by a guy named George Woodwell. In 1985, he left and founded the Woods Hole Research Center. So that's where I am now. I actually worked at the Marine Biological Laboratory for 10 years before going to the Woods Hole Research Center. And I'm also adjunct at WHOI, Woods Hole Oceanographic. So I think probably my only distinction is having some affiliation with all three of those places in Woods Hole. There's also USGS, U.S. Geological Survey, National Marine Fisheries, and Woods Hole. So there's this whole collection of scientific institutions in the small village of Woods Hole. At the Woods Hole Research Center, we focus on climate. We work on the land surface. We're mainly terrestrial scientists. We work on land and water, but not so much the ocean. And we do both what I call defining the problem. We do the fundamental science, trying to understand how the Earth is changing, how climate change is working. But I think something that sets us apart in some ways is that we also spend a lot of time trying. Do I need this? I'm not even sure this. Okay, I do. Yeah, okay. We spend a lot of time trying to shorten the gap between the science and what we hope is wise application for public policy. And it's this combination of attributes, I think, that actually for the last 4 years in a row, we've been named the world's #1 climate change think tank, which always kind of strikes me funny. I'm not even sure what a think tank is, and I don't think we're one of them. But at any rate, we're happy to continue to get this honor. Out in the front, I think, on the concession stand, I put some flyers and various information that I would encourage you all to grab. I also put a sign up for our newsletter, and one of the reasons we like to do things like this, to get out and talk to people, is to get people to sign up so we can send our monthly newsletter out and help spread the word about the work that we're doing at the Woods Hole Research Center. So I don't know if anybody has signed up yet. Please do when you go out. I actually have to leave before the end to catch the ferry, the last ferry to get back to Woods Hole, but they'll get to sign up to me, so please sign up on your way out. All right, permafrost. Permafrost is technically defined as ground that's frozen below 0 degrees Celsius for 2 or more years consecutively. In practice, it's often been frozen for hundreds and thousands and even tens of thousands of years. This is an eroding permafrost cliff along the Kolyma River in Siberia. I've worked there for many years. You can see this sort of shiny ground here. This is what's called the ice wedge. This is just a frozen mass of ice in the ground. And in this case, we can radiocarbon date the carbon, the material in this permafrost, and it's been frozen for about the last 30,000 years. One way that really gets hammered home, so I've been to this site maybe 10 times, and I've walked along the bank of the Kolyma River down here at the sort of the base of this cliff, and every time I've been there, you find bones of woolly mammoth and other long extinct beasts. And you can date those too, and they're all 25 to 30,000 years old in this site. You can also look closely. So this is, again, the same site looking very closely at that eroding permafrost cliff. And you see these things, which are just roots of plants that lived also 30,000 years ago in this case. And a plant around here or in the tropics that dies very rapidly, the roots decompose, the leaves decompose, the wood decomposes. But permafrost, because it's frozen, this material just stays in a pristine state. Sometimes it will partially degrade. Lots of times it partially degrades. Other times it's almost just like it died, that year or something like that. So what happens, although plant productivity in the Arctic is low, plants don't grow very fast. They decompose, they rot even more slowly. So over year after year after year, decade, century, millennia, lots of carbon builds up in the soil. This map just shows the distribution of permafrost in the northern hemisphere. It's about a quarter of the land surface in the northern hemisphere is underlain by permafrost. Big parts of Canada, Alaska, and the largest masses in Russia. And the film that we'll see tonight, which I haven't seen, I'm really excited to see, is in Dawson City. So that red dot is Dawson City on the Yukon River. As Gary mentioned, I do a lot of work on the Yukon River farther, closer to the mouth, near where it dumps into the Bering Sea. But I'd love to get to Dawson City one of these days. When you think about what's going to happen with permafrost in the future, it's important to recognize that, well, the Earth is warming, but the warming is 2 to 3 times greater in the Arctic. So that's what this figure is illustrating. It's showing the deviation from the long-term mean of Earth's temperature. The redder colors, the deeper red colors, are greater warming. You can see that it's essentially warming everywhere over this period, but the warming is greatest in the Arctic. In terms of what's going to happen with permafrost moving forward, there's already permafrost thaw going on. These are different model projections, different model scenarios about what will happen with permafrost over the remainder of this century. Sort of a best case, a middle case, and a worst case scenario. Best case being if we get our act together and get off fossil fuels and so on in a hurry. Worst case is more like a business as usual scenario. But what this shows is even a best case scenario, we're going to lose about 1/3 of the near surface permafrost over the remainder of this century. A worst case scenario is more like 70%. So there's still a big gap. There's reason to act to track along the best case and not the worst case, but in any event, we're going to continue to lose permafrost moving forward. I often like to talk about sort of this cycle, both how permafrost or how climate change or global warming impacts permafrost and how the changes that happen when permafrost thaws. So across the Arctic, you see where permafrost is thawing, human infrastructure is collapsing, buildings are sinking into the ground, roads are getting wavy. It's also impacting vegetation, plants, it's animals, and the people that live in the Arctic are being impacted by permafrost thaw. But the other side of the coin is how permafrost thaw can feed back to the global climate system, and that's what I spend more time thinking about. And the way that happens is through the release of greenhouse gases, carbon dioxide and methane, this organic matter, this carbon that's built up in permafrost, again, over millennia. When that permafrost thaws, that material starts to rot, to decompose, and it releases greenhouse gases, carbon dioxide and methane in the process. Now, I want to tell, I guess, what I call a little story to help you understand how carbon dioxide in the atmosphere has changed over time. And I'm going to do this by showing photographs of my ancestors. I'll show a series of them. So this is my great-great-great-grandmother, and each of the photos I'll show, the number at the bottom is the year of birth, and the number on top is the carbon dioxide concentration in the atmosphere when that person was born. So when my great-great-great-grandmother was born in 1820, carbon dioxide, this main greenhouse gas, carbon dioxide concentration was 284 parts per million. My great-great-grandfather was born in 1847. CO2 concentration was the same. And in fact, you can go back for about the previous 10,000 years before that, look at the record of carbon dioxide concentration in the atmosphere. We know we can make those measurements by looking at CO2 gas bubbles trapped in ice cores. We can go back even farther than that. But for that 10,000 year period, carbon dioxide concentration never varied from around 280 parts per million. Sometimes a little more, sometimes a little less, but always right about there. Let's see, where are we? My great-grandfather, born in 1873. Not much of a change, maybe ticking up a little bit. Grandfather comes along. Looks like we're starting to see a change. My mother, and then I come along. So we have sort of 3 generations with no change, 3 generations where we're going up at about 3 parts per million per decade. My son comes along 40 years later, and we get this big jump. My daughter a few years later, and now today we're at about 410 parts per million. So it's kind of interesting. You can see we're now increasing at more than 20 parts per million. Very rapid increase. It's interesting to think that before a few years ago, no human who had ever lived had ever breathed carbon dioxide in the atmosphere higher than 400 parts per million. It's never happened in the history of, the 150,000 years that humans have walked the face of the earth. And it's unlikely that any human who's alive today will ever breathe carbon dioxide that's below 400 parts per million. But the big question is, what happens moving forward? Does it continue to increase at the same rate? Does it slow down? Does it level off? The answer to that question depends on several things, probably most importantly, where do we get our energy? Do we rapidly transition to renewable energy sources? This is an aerial shot of the main building at the Woods Hole Research Center, where we get essentially all of our energy from wind and solar. Or do we continue to rely heavily on fossil fuels, coal, oil, and natural gas? It also depends on how we treat and manage Earth's forest. This is a shot in the Amazon, intact canopy, intact forest that goes on for hundreds and hundreds of miles. These forests store lots and lots of carbon. They're pulling carbon dioxide out of the atmosphere. Do we leave them intact? Do we restore them where we can? Or do we go the other direction? And this site here is just a couple of miles from the site in the previous slide. A few years before this photo was taken, it looked identical. So it was an intact forest. The trees are cut down to plant soybeans to ship to Europe and China to feed animals for us to eat. Why is one tree left? You see this in lots of places where you get these massive clear cuts. This is in Brazil. This is a Brazil nut tree. They're protected. You can chop everything else down, but not the Brazil nut trees. And it also depends on what happens with permafrost. So fossil fuels get a lot of attention. Deforestation gets a lot of attention. When people are thinking about what's going to happen with climate change moving forward, they're generally not thinking about permafrost. But there's an awful lot of carbon locked up there. When permafrost thaw accelerates and continues, some of that carbon is going to go to the atmosphere and contribute to global warming, to climate change. All right, I want to just give you a few numbers to illustrate the magnitude of carbon in some of the different pools that are on land that could end up in the atmosphere. So first of all, this 850 billion tons, that's how much carbon is in the atmosphere right now as carbon dioxide. So that's essentially, that's a 43% increase since the pre-industrial period. So it was a lot lower. We've pumped a lot in there. But right now, there are about 850 billion tons of carbon in the atmosphere. In all the vegetation on Earth, all the plants on Earth, it's mainly forests, mainly in wood and trees is where the carbon is. There are about 5 100 billion tons. So when we chop down forests, that carbon goes to the atmosphere, leads to more warming. When we let forests grow or we restore forests, photosynthesis pulls carbon out of the atmosphere. So this can go either direction in the future. You know, this amount of carbon in forests can decrease if deforestation accelerates, or it can increase if we let forests grow and we restore forests. Fossil fuels left in the ground that we could get to should we decide to continue to do so. So that's coal, oil, and natural gas are about 1,200 billion tons of carbon. So more than is in the atmosphere right now, a bit more than twice as much is in all the vegetation on Earth. And then permafrost, this thing that doesn't get as much attention, has about 1,500 billion tons, 3 times as much as in all the vegetation, almost twice as much as in the atmosphere. So this massive pool of carbon that, again, slowly over a millennia, many thousands of years has built up because decomposition in the Arctic is so low. But as permafrost is thawing, it's just as if your freezer at home, if you put food in your freezer, it's going to stay there frozen as long as your freezer remains a freezer. If it turns to a refrigerator, it starts to rot, and that rotting process is releasing carbon dioxide and methane, greenhouse gases. And that's what's starting to happen in the Arctic. All right, how much carbon might be released from thawing permafrost? How much carbon can this actually put into the atmosphere to contribute to climate change, to global warming? This is kind of the science that we're working on every day now. The best estimates are over the remainder of this century, something like 130 to 160 billion tons are possible. That's a hard number to wrap your head around. What does that mean? Right now, all the human activities in the United States are putting about 1.4 billion tons of carbon into the atmosphere each year. So that's transportation, it's heating, it's everything that we're using fossil fuels from. The U.S. is putting about 1.4 billion tons into the atmosphere per year. So this is essentially like bringing a whole additional United States online as permafrost thaw accelerates over the remainder of the century. Right now, it's roughly in balance. Over the last many thousands of years, permafrost has been accumulating carbon. Right now, it's roughly in balance, but we're tipping toward it becoming a source, and it's going to become a bigger and bigger source, I'm afraid. And the fact is, most policymakers aren't thinking about permafrost. They're thinking about fossil fuel, reducing fossil fuel use. They're thinking about reducing deforestation, but this thing hasn't been on their radar screen so much. So what needs to be done about it? Well, there's still a lot of science to be done. That's what we spend most of our time doing in the Arctic, studying permafrost, refining the estimates of how much carbon is there, how quickly permafrost is thawing, how quickly the carbon decomposes and releases when the permafrost thaws, and also whether it goes off as carbon dioxide or methane. That's an important distinction. I won't go into those details, but if it's going to be released, you'd rather have it go as carbon dioxide than methane, and we're trying to figure out that balance. But we're also working hard to get the science to the policymakers, not just write scientific articles that other scientists read, but to try to get this information to policymakers so that they can act on it. We work a lot at the international level, the United Nations Framework Convention on Climate Change. We go to all those meetings. Paris climate negotiations, we were there trying to get the information to those folks. We have worked a lot at the federal level. Our director in 2008 was John Holdren, and then President Obama asked him to be the White House Science Director. So he was in DC for the 8 years of the Obama administration. He's now back in Woods Hole. But during that time, we had really good connections both with the White House and the State Department, and we advised for a few months the State Department as they were preparing for this glacier conference in Alaska in August of 2015, feeding them information about permafrost and why it was important for the climate negotiators to be thinking about permafrost as they were prepping for the Paris climate negotiations. So I was there in Anchorage at the time of this conference, and it was really thrilling to watch our president at that point basically saying the same kind of story I'm telling you right now, how much carbon is in permafrost and how some of it's going to be released and accelerate global warming and how we need to act on that. You can imagine we're not having quite as tight of connections with the federal government right now, but we're still happy to talk if the phone rings. And then we want to try to get the science not just to policymakers, but we look for any opportunity to tell the story to whoever will listen. So we're always happy to get invitations like this one tonight and come to groups like you and talk about our science. Any way we can get the story out, we try to do it. And my final slide is one of the ways that I'm really excited about right now, and it kind of ties into what what this place is all about. That is, we're working on a short film about permafrost and about this group of students who spent several weeks in the Alaskan Arctic last year. It's actually a project that happens every year where we take a group of undergraduate students, some grad students, some scientists, study permafrost in the Arctic, train the next generation of scientists, and hopefully communicate that science to broad public audiences. And so this film that's being worked on is called Permafrost Now, and it will premiere next month at the EarthX Film Festival in Dallas, and from there we'll go to the Mountain Film Festival in Telluride, and then we'll see what happens after that. Hopefully we'll get a chance to show it here. So thanks for your attention, and I, like you, look forward to watching the film.